coding. Okay, let's get started. So this time we go over this a bit complicated proof showing that all kinds of measurement we talk about can be formulated as a computational basis measurement, because if you computationally they are the same, because you can add an ancillary system and do this entangled unitary U that depends on the measurement you want to do, and create some weird entanglement between your system and this ancillary measurement system. Then when you just do a computational basis measurement on the ancillary system, that will effectively be the generalized measurement you want to do on your original system. And yeah, the proof is a bit technical, but basically we show that this unitary we define makes sense because it preserves length, and we say that it's possible to construct it, and after you construct it, it will do the thing you want. Okay, and so let's finishing the lectures on measurement for now, and we jumped into this other topic. So it's the application of entanglement. Okay, so we are going to talk about two protocols that use quantum entanglement to do something that seems weird, that seems to be hard that's not quite possible with classical communication. Okay. So the first one is superdense coding. So here the task is very simple. There's Alice and Bob, and Alice wants to send some string to Bob. And in terms of efficiency here, we want to send as little bits as possible while still having all the information to Bob. So instead of sending a classical bit string, we want to send a whole bunch of qubits from Alice to Bob, and want to see, okay, and here is a very simple case, so there is no error and no malicious puppy in between. You just send things through, and you want everything to be perfect. And so this superdense coding is called superdense because we see that when you send a qubit, your information density is more dense than classical information. If you just send one qubit, then you can send two classical bits of information. And this is done by using this shared entangled state. Okay. So the shared entangled state is a state that's a 2-qubit state, and mathematically it's in this 0, 0 plus 1, 1 vector. But the weird part about this is that this 2-qubit state, one qubit is getting held by Alice and another is getting held by Bob. And yeah, Alice and Bob may be physically really far away, but we still think it's possible to have this 0, 0 plus 1, 1 state. And hopefully you can already see here that this thing has some kind of correlation, because let's say when you measure in a 0, 1 basis on Alice, so when Alice measures 0, then this thing will collapse into 0, 0, and Bob will also measure in 0. And if Alice measures in 1, and Bob probably will also collapse into 1. So you see that this has some kind of correlation, like shared randomness, but we are going to see very soon that this is more powerful than shared randomness, because in even if you have shared randomness, you cannot send one classical bit to send two classical bits. Okay, that's not possible. And but it's also like shared randomness that this thing has no information. Yeah. And it's just randomness. Okay, so that's back to our quantum protocol superdense coding. So Alice wants to send 2 bit to Bob, and here we just write down, just give a label to our 2-bit information. So the 2-bit information can be 00 or 01 or 10 or 11. Okay. And then the classical start. Okay. And okay. So the protocol is, so there are 4 possibilities because there are 4 possible messages Alice wants to send. So the first step has 4. Alice needs to do one of the 4 depending on what are the possible message. So if the message is 00, then Alice do nothing. And here the thing we want to keep track of is this shared entangled state here. Okay? So so the model here is kind of Alice and Bob share those 2 things, and Alice has 2 classical bits here. So it's either 0001, 10, 11. And Alice will do something here and send a classical bit. Then send a 1 qubit. 1 qubit. Yeah. 1 qubit later. Okay. But we are in the first step where Alice do something with this thing. So basically the protocol is Alice going to do something depending on which which message she actually want to send. Then send this bit to Bob, and Bob will do something. So on the things Alice do on her side. So first Alice, if it's 00, then Alice do something. And if the message is 01, then Alice apply a Z gate on this qubit. Okay. And so here is the end result of the global state between those 2 qubits that will be. But let's do so this is a good example. Let's do this slowly to see how this actually works out. So Alice apply a Z gate on her part. So in terms of this 2 qubit, that actually means we are applying the Z tensor I gate on that 2 qubit. So we are applying Z tensor I on this side state, that's 00 plus 11. So let's do this slowly, just as an example. So Z tensor I, okay, and this 1 over square root 2 is kind of annoying, so let's omit it for now. So Z tensor I 0 plus 1, 1, remember. And then remember this entangled state is still a linear space. So this matrix multiplication should follow distributed law because and okay, so it's Z tensor I 0, 0 plus Z tensor I 1, 1. And then remember, so when everything is tensor together, then we say that this matrix propagation on the tensor space is just each slot do its own thing. So the first part will become Z on 0 and I on 0. And remember Z is, okay, so Z gate is 1, 0, 0 minus 1. And the X gate is 0, 1, 1, 0. So Z on 0 is 1 and it will do nothing. And similarly, Z on 1 will give you a minus sign. Okay. So that's 0 and I will just do nothing. So 0 and 0 plus and minus 1 times 1 and 1. Okay. Then finally we can put things together. So yeah, so that's 0, 0 minus 1, 1. Okay. Now probably don't need this. Okay. And yeah, then you multiply everything by this vector of 1 over square root 2 because everything is linear, so you can just scale by a constant. Okay. So that's how you see when Alice applies z gate on her part, the global state becomes this 1 over square root 2, 0, 0, minus 1, 1. So yeah, so this is the important thing we'll keep doing for next few lectures or throughout the whole class. So any question on this? Everyone follow how to do this calculation on tensor product space. This is how you do calculation on entangled state. And yeah, going to be important throughout the class. Okay, yeah. Well then, so we're back here. Then, so Alice applies z on her part, then it becomes this 0, 0, minus 1, 1, and here, yeah, let's talk about this. Then you can see that, yeah, let's go back one level. So the next possible label is Alice wants to send 1, 0, and when that happens, Alice will apply x on her part. Okay. And you can see the similar calculation should happen. So you have x here, x here, x here. And remember x is 0, 1, 1, 0. So x applied on 0 will become 1. And x applied on 1 will become 0. So you'll get 1, 0 plus 0, 1. It's in here. Yeah. So that's what happened. When Alice apply x on her part, you get 1, 0 plus 0, 1. And then you can check it yourself. The last one, when the message you want to send is 1, 1, then you should do both. But the ordering here matter. I guess doesn't matter that much because that's just global sign. But anyway, so this is the order we define. And so when it's 1, 1, then we want to do z and x both. And here we say should do z first, then do x. So you can see what happens if you have xz. Yeah. So for example, you will have xz. So now it's something tricky because when you resolve the equation, so xz tensor I and 0 tensor 0, then that's well, z on 0 is 0. Well, let's do this slowly. So this is x0 tensor 0, and that's 1, 0. Okay. And yeah, so be careful. When you apply z, then apply x. But because when you do calculation, you resolve this multiplication from right to left. So z is actually here instead of the other way. But anyway, so you see that xz on 0, 0 is 1, 0. And it's easy to check that xz on 1, 1 is this minus 0, 1. So this is a state, the global state we will have after Alice do the operation. So once again, question on this calculation? Or not? Okay, and there is something else. So those 4 states are actually quite important, so we give them names. We define them. Oh, question.
Yeah. So I can define the other way. First apply x, then apply z.
Yeah. So you want to see what will happen? Yeah. So if you apply x, then apply z, then what happens is you will get a minus sign here. Because you recall xz equal to the x with a minus sign. Okay, so you just get a global phase of minus 1. So I think it really doesn't affect your protocol. just yeah. But okay, so yeah, hopefully I didn't get this. Should be okay. Yeah, and those four states are very useful. So we give an length. So we call this one as beta 00 because this is 00 here, and this one called beta sub 01. This is called beta sub 10, and obviously beta sub 11. Okay, and we are going to give them more names later because they are important. Anyway, so that's four possible global state corresponding to four possible messages Alice want to send. And as we said, the next step is Alice just send this qubit to Bob. So Bob will have those four states. Okay. And then it's done. Then the next step, you are going to prove this in your homework, such that so you are proving your homework because it's easy to check that those four steps are also normal basis. So easy to see that every one of them is unitary length, and every pair between them are also going to each other. And let's see, kind of. So for example, if you do inner product between these two, then you have 0 inner product with 0 minus 1 inner product with 1 so that's 1 minus 1 equals 0. Okay, and or if you have this inner product with this thing, then 0, then they are also gonna write because 0 has no inner product with 1 or 0 1, etc. Okay. So this is also normal basis, and we can before that also normal basis. If your set of vectors are also normal to each other, then they are distinguishable because you can find a projective measurement that project onto this basis. Okay, so there is a measurement Bob can do to distinguish those four probability perfectly. And if so, then Bob know which one of the four he received. Then he know which one of the four messages Alice want to send. Right? And yeah, then that's the protocol. So kind of see that you can, it's hard to tell the intuition, but you can see that Alice can encode her message. So in this one bit, she can kind of encode in two ways. So first you can encode in this classical way, which is just flip her bit, this X, or with the quantum power, she can also encode her message in this phase way, in this Z, like flipping the relative phase between between these entanglement components. You can also encode one bit of message. So, but yeah, it's hard to do very precise characterization of this intuition, but high level, on a very vague level, you can see that we can do simple super dense coding, kind of because we can either encode in this X, which is flip per bit, or she can encode in this phase, apply Z and get a phase between these two components. Okay. And okay, so that's very cool. Super dense coding. We go next. Any question on this protocol? How we achieve this? How we do the calculation? Not? Okay, then let's do some names. Okay, so as we said, and as you probably can feel, this entangled state is very useful. And so this beta 00 is kind of the smallest possible entangled state. And yeah, and because it's the simplest possible entangled state, people like to build all sorts of things on it. And it has a very famous name. It's called EPR pair. Those are three physicists, and the first one is Einstein. And sadly, I don't remember those two, but you can look them up. Yeah. And the historical story here is that Einstein don't believe in quantum mechanics, so he wrote a paper. He wrote a paper with these two other physicists about how you can create this entangled state and send them to two parties very far away and do all sorts of weird measurement on it, and they will have weird correlation. And Einstein thinks that's very unphysical, but then people do experiment and found out that's actually true. So yeah, so people just accept that this weird entangled state is possible, and you can do all sorts of weird quantum thing on it, and we are finding it useful to do communication and stuff. So that's a bit of history, and back to remembering names. So it's called the EPR pairs, and it's also called the maximally entangled state, because so we are not going to tell about how to quantify entanglement, but hopefully you can probably feel that this is the most entangled state you can get on 2 qubit, because compared to, let's say, square root 0.9900 plus square root 0.0111, then this feels a lot less entangled than this one, right? Because this state looks a lot like just 00. Okay? And so this 00 plus 11 over square root 2 called maximum entangled state, because those two components have like the totally equal weight. So it's very far away from any product state. So I guess we haven't defined product state, but product state are just state that can be written as tensor product of two parts. So say 00 is obviously a product state because it's 0 tensor 0. Okay. So this is called EPR pair and maximally entangled state. Well, obviously there are a lot of maximally entangled state, but if you just say maximally entangled state, this is the simplest one that will come to people's mind. So for example, those three other states are also maximally entangled because they also have the same weighting. And actually, the four of them also have names. So those four states are called Bell state, and this basis is called Bell basis because this is something we won't talk about. But there are another experiment, obviously designed by Bell, that shows that these Bell states actually have, or the EPR pair actually have more correlation than possible classically. And so we might cover that if we have time. And anyway, back to notations. Those four states, when you read papers or just read Wikipedias, there are also sometimes people are also written as those four. Okay? So these two are, so this symbol is a capital letter of phi. Okay? And this is a capital letter of psi. And so beta 00 is called phi plus, and this is called phi minus, and psi plus, and psi minus. But we are probably not going to use this. This is just here so that, so that you don't get confused when you read some literature. So those are names, and so once again, let's talk about entanglement. Although we have talked about this a bit. So the first thing is that this chain entanglement or the pre-shared entanglement, it doesn't contain information. So what I mean here is that, so Alice has some information, so say those 2 bits she want to send to Bob. But when Alice and Bob create this chain entanglement, this doesn't depend on these 2 bits of information at all. Right? So this chain entanglement is just a constant thing that doesn't depend on what the information you want to share. And so that's very nice. So that means that Alice and Bob can create this shared entanglement before Alice knows what she wants to send. So maybe there is some downtime that they have lots of time to create this shared entanglement, and there is some burst of message. So maybe Alice start to streaming something, then she can use the pre-shared entanglement to do super dense coding and send information very fast. And yeah, and the second part is that, as we said, the shared entanglement is a lot like shared randomness, right? So I guess, so the shared entanglement 1 over square root 2, 0, 0 plus 1, 1. And it's like shared randomness because if Alice measures the 0, 1 basis, then the state collapses to 50%, 0, 0, and 50%, 1, 1. And that's just shared randomness, right? So either Alice and Bob both have this 0 bit, or they both have this 1 bit with 50% and 50% probability. So I guess a more precise way to say this is that you can simulate 1 bit of shared randomness with 1 shared entanglement, 1 pair of shared entanglement. And also, as we see, it's more powerful than shared randomness because you can easily show from classical theory, that classical information theory, that if Alice and Bob, even they have shared randomness, it's not possible to send 2 bits of information, which is just 1 bit of communication. I guess, okay, it's actually a little trickier if you want to do this very careful, because they are only actually sending 1 qubit. So you need to say with shared randomness, it's not possible to send 1 qubit to send 2 bits of information. But okay, so that will require some quantum information theory to show, but you can show that. Okay. So that's that. And then if you want to think about more practical things, we need to think about how to create EPR pair. And well, now there's the communication, so the limiting factor is how you move things around. And yeah, as we said, the simplest possible way to create this is just by using 1 bit of communication. So Alice will create this shared pair locally and just send 1 bit of them to Bob. Then they will share this pair. And this is in very idealized, very idealized situation. We're assuming that Alice and Bob can hold this pair for arbitrarily long time. They don't decay, which is not quite true in the real world, because I believe right now the quantum computer we have, or the quantum storage we have for storing quantum information, survive probably less than 1 second. But we are in idealized world. We assume because physically, in physical principle, we think this is possible. They can just create this and hold this for a really long time. Okay. And yeah, and back to the very theoretical calculation of the cost, then we see that you can use 1 bit of communication to create 1 pair of shared entanglement. Yeah. And yeah, finally, we see that this can be sort of as a resource. We're going to say about this more later. But here we see that we consumed a pair of shared entanglement to do this 1 bit of superdense coding or 2 bits of superdense coding. Yeah, because you see that after you do this protocol, then you used up the shared entanglement because this pair got modified and sent over. So they now share 1 less pair. Okay, so it's a resource that you can use. Okay, so that's superdense coding. Then let's talk about the next protocol, that's teleportation. And so this is a bit weird. So this is something that you only want to do when you have quantum computer. So it's Alice want to send a quantum state to Bob. And for now, we just say this state is 1 bit, because when you have many bits, you can just apply this protocol to each bit separately. Okay. And okay, but the hard thing here now is there are many hard things. So the first hard thing here is Alice want to send this qubit to Bob, but they only have classical communication. So now how is this possible? How do you send 1 qubit, 1 quantum bit to the other side when you only say classical information? And let's say this bit is psi A0 plus B1. So maybe you say, okay, maybe we do this slowly. And so this bit is characterized by this A and B. And how about we just send A and B through this classical channel? And well, that's possible, but that requires you to actually know A and B. And so we kind of hit on this before, that the quantum state, if you just have the quantum state here, yeah, if you just have a quantum state here, then it's actually pretty hard to know what that quantum state is. So there are many situations that you can get a quantum state here, and there are things called unknown quantum state. So it's a quantum state here, but you don't actually know A and B. And if you want to do measurement to know the A and B, then the state will collapse. Then you no longer have the state. So that's something very delicate and hard to handle. So now the question is, if you have this unknown quantum state unknown to Alice, then how does she send this to Bob? So how do you send something that you don't know to other people? And without actually throw this to Bob, because you cannot just throw this quantum state to Bob, because they don't have quantum communication, they only have classical communication. Okay? And okay, so then this case is called teleportation. It might be a little different than what you imagine as a teleportation, but it is called teleportation. So Alice and Bob will do something, and at the end of the protocol, Bob will hold this side, will hold 1 qubit that's also in this A0 plus B1 state. Okay? Yeah. So yeah, so it's sending unknown quantum information. I guess this is a little implied, but so send unknown quantum information by classical communication. And yeah, once again, we will need to use this entanglement. Okay. So we assume Alice and Bob share this entanglement state, beta 0, 0, and then it is 0, 0 plus 1, 1 state. So now our world has 3 qubits. So Alice holds 2 qubits. So the first one is the state she wants to send, is this A0 plus B1. And that's called is register A0, A1. And then there is another qubit that's sharing entangled state with Bob. Okay, so this is A2 qubit and this B qubit, they are in this state. Okay, and yeah, then let's describe the protocol. So the protocol starts with the global state being psi tensor beta 0, 0, and yeah. The write out is A0 plus B1 tensor 1 over square root 2, 0, 0 plus 1, 1. So nothing happened yet. Okay. Then we do the distributed log because tensor product is a product. So we multiply all everything. And also we change A to alpha. Okay. So I should say alpha here. We change AB to alpha beta. Okay. It should be alpha beta. Alpha beta, sorry about this. But anyway, yeah, you can multiply them out, then obviously you will have those things. So this is 0, A 0, 0, 0, A 0, 1, 1, and beta 1, 0, 0, beta 1, 1, 1. Okay, so nothing really happened. And then Alice, so the thing will happen is Alice will do something here, do a measurement and send result to Bob. Okay. And Bob will do some correction. So Alice will do some 2 qubit operation on her 2 qubit she holds. And the first thing she will do is this control knot. This is really, so we are skipping a little ahead of time. So this control knot is usually like the control knot you think about in classical circuit. But it, so I should say is just control knot if you apply the computational basis. So remember, control knot is a gate. You can apply 2 classical bits. But yeah. So on classical basis is on computational basis, this control knot gate is the classical control knot gate. And 2 quantum bit is actually is defined by just extend that gate to unitary. So basically having everything in superposition. Or let's write it out is this is easier to write out this matrix. So it's a 2 by 2 matrix because it's on 2 qubit, and so it's control knot. It means that if the first qubit is 0 or first bit is 0, then it do nothing on the second bit, so it do this 1, 1 thing. And if the first bit is 1, then you flip the second bit, right? So this is kind of the classical truth table of C0, and yeah, and when it's a quantum gate, we just think it's this matrix. Okay. So yeah, but its operation on computational basis is very clear. Is controlled knot. So if the first bit is 0, then you do nothing to the second bit. If the first bit is 1, then you flip the second bit. So you can see what they do here. Okay. So and yeah, so you apply control knot on the first bit on those 4 states and then see what happens. And we skip ahead. So you can see. So for example, you apply control knot here. Okay, C knot. Then then because the first bit is 0, then you do nothing on the second bit, and also the same thing here. So those 2 components doesn't get changed. And when you apply control knot on here, Then the first bit is 1, so you flip the second bit. So this become 1, and this become 101. Okay? So the global state become those things. And then Alice apply the hidden market that we keep talking about on the first qubit. And remember, well, hopefully, I guess I didn't quite talk about this, but you can check this is true. So Hedma apply on 0 will give you plus state, and Hedma apply on 1 will give you a minus state, which is 1 over square root 2, 0 plus 1, and 1 over square root 2, 0 minus 1. And well, you can do a calculation. We are a bit short on time, so let's do this faster. Okay. And yeah, so let's just check one of them. Let's check a third of them. So apply Hedma here, right? So this 1 will become minus, and which is 0 minus 1. So you get 0, 1, 0 minus 1, 1, 0. Okay? And all other 4 has a similar thing. And you will get extra 1 over square root 2, which combined with this 1 over square root 2 become 1 over 2. And now we just group things together. So because the prefix now there are 8 different components, but we only care about what they are on the first 2 components, so we group the 0, 0 together. So for example, this 0, 0, 0 and this 0, 0, 1 can be written as 0, 0 and alpha 0 plus beta 1. Right? This is a distributive property of tensor product again. And similarly, let's say 1, 1. Then for the 1, 1, you have this alpha 1, 1, 1 and this beta 1, 1, 0. And so it's alpha 1 minus beta 0, etc. Okay. And so why do we want to write them in this way? Because on the third step, Alice will measure in computational basis. And yeah, so we'll rewrite it in this way. And you can easily see that when she measures in computational basis, she is going to project into those 4 things, right? Because, yeah, you want to see whether the first 2 qubits are either in 0, 0, 0, 1, 1, 0, or 1, 1. Yeah. So when Alice do that, what happens is the global state is going to be projected into those 4 things. And the probability that happens is the amplitude square of those 4 states. And you can easily see that, well, the amplitudes are actually all the same. They are all 1 over 4. So that's 1 over 2 square plus the amplitude of those things. Those 4 things are all amplitude 1 because that's alpha square plus beta square. Okay? So when Alice do this measurement, the 4 outcome has the same probability. And then we'll have 4 different post-measurement states, right? So just those 4. So when it's 0, 0, the global state will project into this thing, and yeah, and so alpha 0 plus beta 1, alpha 1 plus beta 0, alpha 0 minus beta 1, alpha 1 minus beta 0. You can check the calculation to see that I didn't make a mistake. And okay, so those are a bit mysterious. So why do we want to do this CNOT and Hedema measurement? And they are actually more structured here. So you can check this, that the first 3 steps we do here is actually a measurement in Bell basis. So the Bell basis are those that we talk about. Okay? So yeah, you can check it out. So basically this is CNOT and Hedema operation is a unitary change between computational basis and Bell basis. And when we do this, we basically mean Alice do a measurement in Bell basis. And anyway, so what will happen is that well, the first state will happen all with equal probability, and Bob's side will get collapsed into something, one of those four. And now you see that the good thing about this is those four things now has very high correlation with the state we want to teleport. Remember, the state we want to teleport is alpha 0 plus beta 1. And here we already see alpha 0 plus beta 1, right? So if the measurement outcome is 0, 0, then we already win, because Bob is holding this. So Bob gets that, yeah. And but what if the measurement outcome are the three different things? Well, there are also alpha something plus beta something, or alpha something minus beta something. But that can be turned into alpha 0 plus beta 1 if we know the measurement outcome. Okay? So yeah, so this is the thing we do. So if it's 0, 0, we do nothing, and let's just check one of them. So say the result is 1, 0, then Bob is holding this state. And if Bob apply a Z gate, then that will get a minus sign on this one state, and so you get alpha 0 plus beta 1. Okay, so that works. And okay, let's also check this. So if Bob is holding this state, then Bob can apply an X gate that will start between 0 and 1. So he will also get back to this state. And then you can see that when it's 1, 1, then Bob can do this ZX, and he will get this state. But okay, so the tricky thing is Bob need to know, but those four states are not orthogonal. So if Bob doesn't know the measurement outcome, then he cannot correct back because he doesn't know how he should correct. But if Alice also sent, so Alice sent 2 classical bits to Bob, and then Bob know which one of the 4 it is, and Bob can correct it. And we can do this in more organized way. So let's say the 2-bit Alice sent is called M1 and N2. Then Bob will apply this X to the M2 gate and Z to the M1 gate. And yeah, so that's teleportation. And we have 2 minutes. Yeah, we can probably finish the last few parts. Oh, I guess first anyone has a question about how teleportation is done? If not, okay. Yeah, so here we see some weird thing about entanglement. So yeah, the collapsing of state really happen immediately. So remember, Alice and Bob can be really far away. Alice can be at this classroom, and Bob can be at like maybe on Mars. Okay, so we are really far away. Even speed of light, they require some. Maybe Bob is 100 light years away, but we think that when Alice do a measurement on this part, then Bob's state also still collapsing into the one of the 4 state immediately, even though it's impossible to send information faster than speed of light. But the collapsing of state has no information, so it's okay. And yeah, so this is the next part. So Bob cannot learn anything about psi until he receives N1 and 2. So this collapsing of state really don't say information. I don't think we probably don't have a discussion, so let's close this out. Okay, yeah. So yeah, so it's really interesting. So okay, so something really interesting happened when the measurement happened, because when Alice do this measurement, will create one of the 4 measurement outcomes that's totally random. This has no information about with alpha and beta, right? Because this just all happen with 1/4 probability, doesn't depend on alpha and beta. So after Alice do this measurement, Alice don't have any information about psi. And as we said, because Bob is really far away, Bob also don't have any information about psi. Okay, so the information about psi kind of disappeared from the universe, getting separated into this N1 N2 measurement outcome and Bob's unknown post-measurement state, and it only reappears once Alice sends the information to Bob. Once Bob receives the information about N1 N2, then he can correct his state back to psi. But just right after the measurement, Alice doesn't know anything about psi, and Bob doesn't know anything about psi. Just what quantum mechanics do. Yeah. So you can think about that, and yeah. Okay, we are a little over time, but you can see that Alice's copy of psi got destroyed, so this doesn't give you cloning. Okay. So sorry about overtime. Any question? Otherwise, let's start on Thursday. Okay? Yeah. Okay, see you next time. Stop.